So let's talk about topological ordering. And we must first understand what an order is, right? There are more orders than there are more types of ordering than simple numerical ordering, i.e. increasing or decreasing. There are all sorts of ordering in mathematics. So a order in its most theoretical sense is is something on a set X and is a binary relation on X such that it is transitive. For instance, if X is less than quote unquote ordered less than Y, then and Y is ordered less than Z, then X must be ordered less than Z. Okay, so order has to be transitive, and for any XY in the sets, then exactly one of the following holds: either X is ordered lower than Y is lowered order than X, or X and Y are ordered equally. So let's just recall for a moment our convention about writing edges, namely that in a undirected graph, a edge is a set because it's the order of vertices is irrelevant. The edges are undirected. In a directed graph, a edge is a ordered tuple. Okay, and it's written in so many different ways. And literally every textbook you pick up, you will find a new notation for writing edges. Um, I really, really, really wish Knuth would like release the Principia of Computer Science and just define the notations firmly. Um, but until that day, you're going to have to just slog through all the different notations that exist. And these are the three most common ones, although there are others. Okay. Um, so, a topological ordering of a graph VE is an ordering on the vertices such that if there is an edge U to V, then U is ordered less than V. Okay, so this is exactly what we talked about when we defined directed acyclic graphs, that we could order the vertices so that there is a natural flow from left to right, up to down. Okay, so the question becomes, how do we get a particular topological ordering? And that, as algorithm students, is what we want, what we're most concerned with. How can we implement an algorithm that gives you the topological ordering? And ideally, we want to do it in O of n plus m time, in linear time. Okay, ideally. So, how do we do that? Well, there's a couple ways. There's a couple algorithms that allow us to do topological ordering, especially in linear time. But what's the thing we talked about when we talked about the flow, when we first defined DAGs and we talked about the flow of the DAG, when I showed you the different graphs and how they may be rearranged to make it obvious that they are directed and acyclic. We talked about sources and sinks, right? So what do we know about the ordering here? What do we know about this first vertex? What condition can we exploit? Well, we know that in a topological ordering, the leftmost index must be a source, right? There can't be any incoming edges, right? So perhaps there's something we can do with the in degree of the vertex. And in fact, that is our key to finding the topological ordering. The leftmost element has to be the source of the entire graph, has to be a source in the graph, okay? No incoming edges. Then the next element, well, it could be a different source, or it could be a node where the incoming edges are only from vertices that are to the left of it, right? So once we put this vertex into topological ordering, what we could do is remove these edges and allow our algorithm to place this vertex next in our topological ordering. So that is the idea behind finding the topological ordering using the integree of vertices. We first count the integree of each vertex. This is like a bit of pre-processing. Okay, how long does this take? This takes O of M, O of M times. Just we need to count the number of edges. Oh, and we if there are a few edges but a lot of vertices, we might need to add an n factor because to allocate list memory and stuff. Okay, and then for each vertex that's a source, we add that vertex to the topological source, and then we lower the integree of all the vertices that this vertex leads to. So that's what we're doing here. We add first the source, the vertices that have no integree. Then when this gets added to the topological source, we don't care if we add this vertex or not, because this edge is covered. So we lower the integree of all the vertices that 1 leads to, namely 2 and 4. And then once this integree becomes 0, then we can add it to the topological sort. And in fact, that's what we do here. So suppose we have this graph here. Okay, and we have the adjacency list. Okay, first thing we do is generate the integree for vertex V. And the integree, we generate the integrees for each of the vertices. So we notice that vertices A, B, and C all have integrees of 0. These are all sources. Then vertices D, F, and G all have integrees of 1. And then vertices E and H have integrees of 2. So what do we do now? We simply go to all the vertices with integree of 0, and we add them to our topological ordering, A, B, C. And then as we're adding them, for instance, and I did that too fast. We first add the vertices that have 0 integree. So we add A to the topological ordering. And then we see all the vertices that are connected that A leads to, namely D and F, and we lower their integree. So D, we lower the integree to 0, and E, we lower the integree to 1. Then we add B to our topological order. We remove B from the list from the vertices that we haven't added yet, and we lower the integree of E. So we take that and lower the integree of E. Then we add C to our topological ordering, and we remove C. And we don't need to lower the integree of any other vertices. Then we add D to our topological ordering, and we remove we reduce the integree of F, so we put that there. Then we add E to our topological ordering, and we reduce the integree of G. And then we add F to our topological ordering, and we reduce the integree of H. Oh, and we were supposed to reduce the integree of H before that too. So H should be here now when we added E. Sorry about that. And then we add G to our topological ordering and remove that from the list. And then we add H to our topological ordering. So our topological ordering for this directed acyclic graph is A, B, C, D, E, F, G, H. Okay, and in fact, if you draw in the edges, you could see why this is a topological ordering for this graph. All the edges go from left to right. It's quite beautiful, really, when you see it laid out like that, right? Okay. Okay. So one thing I want to note is that, as you could probably guess, there isn't only one topological ordering. There isn't one unique topological ordering for any given graph. In fact, the graph that we have here has multiple topological ordering. So we have the topological ordering we came up with. We could also rearrange the topological ordering in a number of ways. Okay? And so ask yourself one question right now. What type of graph would have the greatest number of topological orderings? What type of graph, given n vertices, would have the greatest number of topological orderings? And the answer is an unconnected graph, a graph with no edges. Because if all the vertices are sources, then you could pretty much any permutation of vertices would be a different topological ordering. And therefore, you have n factorial topological orderings in that case. Good. So, so we went over that. We said unconnected graph, and actually, I'm using the this isn't the formal. This doesn't technically be graph with no edges. That's more correct. With no edges. And what is the DAG with the least number of topological sorts for a given number n of vertices? What would be a graph with the least number of topological sorts? And it would just be a path, right? A path. A path. Because if the graph is A, B, C, ... then there's no way to reorder these vertices, right? They have to appear in this order left to right, because all the edges have to go left to right. Or I should say, the most correct thing would be to say a graph, a DAG that has a path of size n. Okay, you have to say a DAG because we don't want because as you can imagine, if the graph has cycles, then it doesn't have a topological ordering. Secondly, you have to say a path of size n because we could have a graph like that. We could have other edges like that go along the same way. That doesn't impact the number of topological orderings either. All right. Okay. So this is the code for literally the code for what we just did. How long does this take? What is the running time? That's always a good question to ask ourselves. And so for each edge, so this takes O of m time, and this takes O of n time. For each vertex, O of n time. And then we have a while loop, and the while loop says while the degree n list is not empty, remove a vertex from the degree n list, and then we append x to the sorted list. And then for each x that's adjacent to the vertex that was just put in sorted, we lessen the degree, and we move the degree, and we move the vertex whose input degree was reduced, we move that to the corresponding input degree list. Okay, and how long does this take? Well, these functions all together touch every vertex once and every edge once. So what does that mean? It means it takes O of m plus n time. Okay, so it's a linear time function. Okay, so hopefully that makes sense. Okay. So important thing to note is that if a graph can be topologically ordered, then the graph is a DAG. Only directed acyclic graphs can be topologically ordered. And this is simply because if there is a cycle present, then there is no topological ordering where all the edges go from left to right. And yeah. And yeah, so again, this is just an explicit definition of topological ordering, and it's simply stating that the topological ordering is simply a numbering of the vertices such that the direction of the edges is maintained. And so the example that we gave earlier, where where there are vertices A through W, the topological ordering is simply the corresponding number sequence that lists the order of the vertices. And like the examples we've done before, the topological order is simply 1 to 23. Okay, so so let's stop there for the definition of topological ordering, and then we'll go on to depth first search, and that has implications for topological ordering as well. Thanks.